In this video, we have a lot to cover, and as expected, some of this will be review. However, I do encourage you to watch the entire video because it sets up an important context to follow the new material. At the very least, it offers a new perspective on what you understand about programming, but at a lower level. Today what we're going to cover is structures, functions, classes, constructors, and destructors, setters, and getters. As we've talked about in the previous video, we discussed variables, and I've stated that they are simply nouns. However, we've mostly worked with common or fundamental data types like integer, char, double, and we progressed to using them with pointers and arrays. In this video, we'll do compound types, which is where we get to create our own data types. The first compound data type to look at is something called a structure. Here we are simply clustering individual variables together into one large variable with its own identified name. In this way, we are deciding on the labeling of its type and name. In this example, you can see I have three variables that have not been initialized. There is a keyword struct and a name part. Here's how we initialize it in a memory model. I'd like you to consider this as a template or a blueprint of the beginning of a struct. The default access of a struct is public, but we'll get to that soon enough. As you know, all variables have a type, name, address, and a value. In a memory model, this is what we would see when we want to initialize the struct for future use. As you can see, the struct also has a name, value, and address, but the type is now defined by us because it is a compound type of other common data types. Note that the struct itself has an address because by definition it is a data type. To use the new struct, we need to instantiate it as part 1. Once you instantiate your struct, you can now initialize your common variables inside your compound type. You can instantiate and initialize in one step as well. So here I've got part 2, and then I can initialize it after instantiation with all of its values. And here it is in a memory model. We've really spent a lot of time talking about variables and how they are also nouns. It is time to talk about another part of programming with its own grammatical equivalent. As this slide states, functions are verbs. In this video, I'm not going to review functions. I assume you have full knowledge of functions and how to create and call them. If you look at a typical function name, they usually are in the form of a verb. And that is for a good reason, because they affect the nouns that we have previously created. Without these nouns, we wouldn't be able to form verbs. For example, a person, noun, runs, verb. They exist together at all times, and as you'll see, we can further combine these two things into a single entity or a combined object. As we did with a struct, we started with a framework or outline. In this example, we'll use the classification dog to illustrate how this works. Our class is divided into two parts: data types and member functions. Pay particular attention to the keywords private and public. This is what allows others to see or access your code. In most programming languages, member variables are typically private and functions are public. You have a third option for protected, but we won't discuss that here. Notice the names of our functions: set, get, and bark. These are verb style words. As I stated previously, we intend to make an object, which is again a noun. And in this case, we are defining the capabilities of that new noun. If you notice the name of the first function, dog, that is a special function called a constructor, and it is labeled as a noun. That's because that is what we call to literally make the noun dog. We'll talk more in a moment about that. I want to take a moment to emphasize an important fact. A class is only a blueprint. It is not an object. It is a blueprint of a dog we'd like to create. You do not walk or feed your blueprint any more than you do not live inside a blueprint of your house. You must understand the difference or you will be forever confused. If we look at the memory model of this class, this is what we see. Here we have no name and no initialized data, nor do we have an address in memory yet. All we have done is defined a new compound type called dog. It is not until I perform instantiation that we can make an actual dog with a name, type, address, and given characteristics for values. But we start with a blueprint and we need to have the compiler create an object for it in memory. I start with the new data type dog, which just represents the blueprint I want to build from. Then I define a new individual name. This has the effect of instantiating the new object into existence. Think of it like sending your design to a 3D printer. After I create the object, it immediately becomes the current object until I create another one. This is now the current object. After creation, I can now take advantage of the actions that the dog can perform by calling its verbs or functions. Here I use the dot operator to call the bark function on Fido. Noun uses a verb. I can repeat this process and create another dog named Rover. Rover will then become the new current object. The current object is often referred to by the keyword *this when written in code. We'll talk more about that soon. I said there was a special function called the constructor. To extend my 3D printer analogy, think of the 3D printer as the instantiation machine, where our code calls the constructor function to actually start the 3D printing of our object from its blueprint. Let's look at this in another example. If I have a blueprint of a coffee cup, can I hold anything in it or drink from it? Obviously not. But I need to start creating my object somewhere, and that place is the class. In this very oversimplified class of a coffee cup, we can see a few variable characteristics we will give each cup. Note, without arguments or parameters in the constructor, it is called a no-argument constructor. There are many cases where you would want to give your object specific characteristics from the moment of creation. And to do this, you can call constructors with actual arguments. Here I am passing the radius and the height of a cup of coffee. Please note, if the no-argument constructor is not written in the class, this two-argument constructor would become the default constructor, and all coffee cups would be 3D printed according to this two-argument constructor, not the one above it that has no parameters or arguments. If no other constructor, this is the default constructor. Let's look at another example one more time. If I take my class, coffee cup, and I instantiate Tim Horton Cup 1, this is what I produce. We can define several variables of a compound type. Each is called an object or an instance of the class. Coffee cup, Tim Horton Cup 2. Same blueprint, but is this the same cup? Again, Tim Horton Cup 3. Cup 4. It came from the same blueprint, but is it the same object? And the answer to that is no. It's not the same object. I'd like to circle back to structs again for one final point. With a struct, you can also use it in a very similar manner as you would a class. However, the major difference is that a struct is by default set to public for both member variables and functions. And yes, with a struct, you can actually add member functions. In a class, the member variables are by default set to private, but in a struct, the member variables are actually set to public. I think it is a very appropriate time to highlight a fact about programming. We start with a variable, and then we can move up a level to a struct, and then again to a class. This is what is referred to as a fractal. And I could give you a fancy explanation of a fractal, but this illustrates the meaning exactly. We are building upon smaller components to make larger components, and so on. We use logical control structures to make our source code into something productive. But that code is really meant to move around or manipulate the actions of our objects. Think of all the moving physical objects in the engine of a car. They all work in unison to produce motion. This is what programming is. With this in mind, let's take a much more practical example of using a class that is familiar to you. We have a class, but no initialization or constructor. This is a great time to note that if you don't explicitly give your class a constructor, it will automatically create one in C++ anyway. However, it is a good practice to always have one in your class. More about that soon. I'm going to go to the main and instantiate a student called Tom. Note, Tom has no initialized characteristics, but you know that he has a student number and he is expecting grades. We expect to be able to have this information displayed, set, and retrieved. We can now also create SIMA. By declaring the member variables private, we are encapsulating the data from open access. It's like putting a box around the data inside the scope of a class. In a sense, it's a box inside a box. Think of it like a locked bathroom inside an apartment. As a way to protect our original state of our member variables, we can use something called a setter function. It is also referred to as a modifier or a mutator because it allows for limited access to private variables, but only enough to see what's there and to set them in values we'd like, while never disturbing their original state. We also have queries or accessors that allow us to use them and see what the state of the member variables are. They are typically void types and are commonly set with a const keyword. You can think of the get as a read-only function as well. Another feature of a modifier function, or setter, is that it can be used for validating a user's input, as seen here in the if-else statement. Why bother with a mutator? It's for an extra measure of control over the user's input. Why use a getter? To get what you set. And lastly, to create a read-only function. Returning to Tom and SIMA, you should understand two very important things. Both objects have their own individual member variables. Only these variables are on the stack. However, both objects share the member functions. They do not get their own individual functions because the functions can be called as needed. In this example, I instantiate Tom, and then I set the information without changing the actual blueprint. And I'm going to display the results as an output with the query function display. Notice I'm using the dot operator to call my function from Tom. As I said earlier, I want to come back to discuss the constructor, but I wanted to do so after discussing the setters and getters. And I hope it will become clear to you why I'm doing it in this order. So a constructor is a mechanism for initializing the data members of an object at creation time. You use it to initialize the object's instance variables. Note the format, the type with the brackets that you would normally see with a function, which coincidentally is also a noun type of a name. If we do not declare a constructor in the class definition, the compiler inserts a default no argument constructor with an empty body. And here's an example. In main, I've got dog, Fido. Coffee cup, Tim Horton Coffee Cup 1. Student, Tom. No argument constructor is not always implemented. If the class definition includes the prototype for a constructor with some parameters, but does not include the prototype for a no argument constructor, the compiler does not insert an empty body no argument constructor. The compiler only inserts an empty body no argument constructor if the class definition does not include a prototype of any constructor. If we define a constructor with some parameters, we typically also define a no argument constructor. That's just good programming practice. The creation of arrays of objects requires a no argument constructor. Each element of an array calls the no argument constructor at creation time. So let's look at this. In this first function is the no argument constructor. In the second function, you see a 2-argument constructor. We also call this constructor overloading or overloading constructors. Overloading a constructor is no different than overloading a function. You can keep the same function name, but have a larger or smaller parameter list, as seen here in these two constructors. That's perfectly legal in terms of writing good software code, and it actually happens in many different languages. The destructor. Some mechanism for tidying up just before the end of an object's life. In case of dynamically allocated memory, an object may need to deallocate that memory before going out of scope. C++ lets us define a special member function called the Destructor that executes automatically at the point of an object's destruction. An object's destructor is called automatically, and it cannot be overloaded, like you saw previously with the overloading constructors. You cannot do that with a destructor. If we declare a destructor in the class definition, the compiler defines the destructor with an empty body. So let's look at this constructor. It has no arguments, and it's set to something called a safe empty state. If we look at the execution time by the compiler, we see that your constructor is called first, and then immediately after, your member functions are called. If you contrast that with your destructor, what you see is your constructor is called, your member functions are called, but it is not until the end of the member function call that your destructor will be started. And it starts execution only after member functions have completed their execution first. So let's look at an example. we have this no argument constructor. And we also have the destructor. Normally you would not see a cout statement in a destructor. You wouldn't see anything in your destructor. But notice in the constructor we have one statement, entering constructor. In the destructor it says entering destructor for student number. So if we instantiate two objects, Tom and Sima, and we call our setters and then the display functions, have a look at the output. First off, for each object we've instantiated, we have entering constructor. Then from the set function, you can see that we've actually output the student number and the grades for each object. But then look at the order in which the destructor is called. If you notice, it's actually calling Sima's object first, and then it's calling Tom's object next. So as we stated previously, the destructor works in the opposite order of creation. Let's look at construction and destruction of arrays. The compiler creates the elements of an array one at a time from its first element to its last, using the no argument constructor. At deallocation, the compiler destroys the array elements from its last element to its first. So it constructs from front to back and it destructs from back to front. So if we look at this example, student A, the output is, if you call the set and display functions, the output is entering constructor 3 times for each of the elements in the array. Then in the order that it was created, but then when we get to the destructor, notice the order that it was destructed was the last element in the array to the first element in the array. So why do I use a constructor when I can just use a setter? And the answer is the object has to first be created before you can interact with it to set variables. In other words, it's how we modify the object after creation. Every member function executes on a specific object, that is, on one particular set of instance variables. We refer to these objects as the current object for that member function. In other words, the current object is the region of memory containing the data on which a member function is currently operating. So if you look at this example again with Tom and Sima, when you operate or you call a function on the first object, which is Tom, so you call tom.set, that is the current object. And then after, when you call Sima.set, that becomes the current object. This holds the address of the region of memory that contains all of the data stored in the current object. This refers to the current object itself, that is, to the entire set of the instance variables. The keyword this is only accessible from within a member function and has no meaning outside member functions. It's important to know that. You shouldn't see the star or asterisk this outside of a member function. If you see it outside of a member function, you should be alerted to the fact that something just isn't right. In this display function, you see an example of returning star this. It means we're talking about the current object, and that's why we're using return star this. Note the difference. We're not using this, we're using asterisk this. In this video, we did a lot of review, or hopefully I've provided a more concrete perspective on classes and how we use them to create objects. Remember, a class is a blueprint, not an object. Nouns are variables, and functions are verbs. And finally, as a new compound type, nouns and verbs together form objects. Thanks for watching this video, and I hope to see you in the next one.